All right, hello everyone. Thank you for the introduction and the invite. So today I'll be talking about this joint work with Ilya Markov and Maarten de Rijke, which is about warm starting contextual bandits via counterfactual learning. So to motivate this a little bit, our setting is that we want to learn a new policy, call it PyW, which is parameterized policy with weights W. And we never want to perform worse than what we consider some safe baseline policy called PyB. And the motivation for this is that we want to warm start the contextual bandit and avoid the typically poor initial performance during learning. So when you start learning, you have a random policy, it will generate random actions, and that's typically bad. So we want to avoid this. So the main idea of the method at a really high level is very simple. You just start running your safe baseline policy and you start collecting data. So you have a stream of data coming in of these tuples where you have X context vector, A is an action, R is a reward, and P is the propensity score. And we assume that our baseline policy is stochastic. And then when you're observing this, you're trying to learn your new policy just via counterfactual learning, right? So you just do your regular IPS, doubly robust. If you want to add variance regularization, you use POEM. Basically, we're just trying to find a good estimate for our PyW through regular counterfactual learning. So we're just trying to solve this equation. And we do this at every sort of time step, capital T. We're going to get a new observation, and we're just going to update this. So we're going to do this via sort of stochastic gradient descent style method. So the next step is in our method is we want to estimate the performance of the learned policy without actually executing it, right? We want to know how well will it work while we're still collecting data from our safe baseline policy. So there has been some work on high confidence of policy evaluation. And basically what we can do here is we can just have the regular sort of IPS estimate of our what we're observing plus some variance term. And this is arguably a really simple one. There are more complicated ones, but for now we're just going to use these. And this is just gives us a sort of upper confidence bound on our newly learned policy in terms of the data that we've observed, right? We can generate a lower confidence bound by just changing this plus into a minus. Very simple. And then the main idea is to just say, OK, we're just going to automatically deploy the new policy and start using it to collect data if there's a lower confidence bound on PyW, the one that we learned, is larger than the upper confidence bound on PyB. So the main idea here is like, what's the worst performance with high probability of PyW that we've just learned, and the best possible performance of our baseline policy, and we just compare these two. And as soon as one is better than the other, we're sort of safe to assume that it works better. So that's the main idea. It's just combining counterfactual learning with these high confidence of policy estimators. So we ran some experiments to test this. So what we've done here is we've taken a basic classification data set and we've turned it into a contextual bandit problem. So what we have is this blue line which goes straight, which is our baseline policy. So we just trained it on a subsample of the data in a supervised fashion. We get a policy that performs OK, but it's not yet optimal. And then we have several contextual bandit baselines, which sort of all start from a random place, right? They have a random policy, and they start learning, and they get better and better and better. Our method, we call it C, starts out performing just like the baseline because it follows the baseline initially, and then as soon as it sort of realizes, oh, we're safe enough to start actually running it, we start following the newly learned policy. So here we compare it just with like online methods, so like lin UCB, Thompson sampling, epsilon greedy, etc. We've also compared it just versus counterfactual learning. So why would we even want to deploy this new policy? We can just follow the baseline policy, we're safe, just try to learn counterfactually. So interestingly, we find exploration helps. So the gray line here is a policy that we just learned through like lambda IPS, which is this new lambda translate IPS that solves a self-normalized IPS problem. And basically, if we just follow the baseline policy and we learn, If we would do this until infinity, sure, we're going to get a really good estimate. Typically, you have to stop after some while. And we see that by actually deploying the policy and having it actively collect data, this helps. Because it can explore favorable regions of the action space quite well. Of course, this heavily depends on your baseline policy, pi-b. So if this policy is pretty good at exploring, then your IPS estimates will also be very high. But if it's not, then this is a good idea. So to conclude, what we're doing is just learning a new policy while never performing worse than a baseline policy. Basically, we're just warm starting contextual bandits by learning via counterfactual learning and then deploying the new policy as soon as we realize it's better based on this high confidence off-policy estimator. And the experimental results, we have more than just this one graph. We have also on ranking tasks that safety is indeed achieved. So that's all I have. Thank you very much.